Hey everyone, I'd like to do a quick review of some important circuit things getting ready for the AP test. So when it comes to circuits, there are the big ideas of EMF and potential difference and current and resistance, and you should all be familiar with those. I'm not trying to go over all the basics, but in order to get ready for the AP test, remember it's going to be a lot more about thinking than doing a lot of calculations. So you're not going to get a huge circuit, and they're not going to ask you, well, find the equivalent resistance of this network of 12 different resistors or things like that. They're going to be relatively simple, but they're often different than the standard thing that you see. You might have to think there's going to be an emphasis this year on at least one of the questions, I'm sure, about measuring and things like that. So how will you measure something like current or potential difference? So remember, those you got to be. Current is measured with an ammeter, and potential difference is measured with voltmeters. We have the whole linearizing thing, which on that resistivity question that I graded, you guys did really well on that, so I was pleased with that. There will be a lot of, there's a good chance there's going to be explaining, so they're going to look for explanations that show your understanding of the ideas for circuits. So, a good way to do that is to make some change in a circuit, and then you explain, what's going to happen, what's going to change in another device or something like that. And they might ask you to rank things. So, when you're using the circuit stuff, the big thing to remember is you have three big tools to help you. You have Ohm's law, which we know is V equals I times R. Remember, if we're dealing with a battery on the AP test, it might also be in the form of EMF is equal to I times R. You have the current rule. So this was the current into a junction equals the current out. Which is kind of common sense. And then you have the loop rule, and the loop rule is your best friend when you do this. So remember, the loop rule is about, and we'll see this in an example here, but basically you choose a direction for the current, and then you choose a path around the circuit, and usually that'll end up being in the direction of the current you picked. And then you want to, the sum of the potential differences equals 0. Okay, and this lets you, this law or rule, if you look at it, really helps you deal with those situations that are kind of foreign. If you stick to using the loop rule, it'll organize your thinking. There's a good chance that it's going to be useful somewhere, and it's going to earn you some partial credit. And then if you can look at the loop rule and then solve for something or see a relationship, it might help you just figure everything out, and you get all the credit, which is of course what we really want. So just some quick examples. So if we looked at a series circuit, this is a basic series circuit. We have a battery with an EMF and 3 resistors in series. Okay, we know that if we use the Ohm's law here, and I'll do it as I would equal the EMF over the equivalent resistance, which in this case would be R1 plus R2 plus R3. That's because these are in series with each other. But just to again remind you about the loop rule, so I always pick a convenient spot. I tend to pick this lower left hand corner since we tend to have the battery right there. So I'm going to call that point A. And so if we talk in terms of the loop rule, okay, if we go clockwise from point A, remember, if you're going this way across a battery, from the negative toward the positive, that's going to be a positive potential difference there. And then as the current, we're going in the direction of the current, so we're going to have potential drops as we go through the resistors. So that minus IR1 minus IR2 minus IR3 is equal to 0. Okay, so that is true. Now that looks more complicated. It's really, if you rearrange it, you can see you end up with Ohm's law from that. So that's not a big deal there. But again, that's the idea, that if we make a complete trip around the circuit from one point back to that point, add up the potential differences along the way, you have to get to 0, because potential is like a state of being. So the potential went up as we travel through the battery, so it has to drop through these resistors and has to get down there at that point. The parallel circuit lets us introduce the other thing. So remember, we're actually going to have 3 currents here. So if we imagine I1 going this way and I2 going through that resistor and I3 going through that resistor, my numbering gets a little confusing, but I think you'll see what's going on here. So we know that if we think in terms of Ohm's law, so we know that Req, or 1 over Req, would equal 1 over R1 plus 1 over R2. And then, so if you wanted to find I1, you could do it that way. But let's just look at the loop rule. So in this parallel circuit, I'm going to start at A again. Okay, so there are 2 paths around the circuit. So we can have actually 2 equations from the loop rule. So you could go through R1 to get back to A. So the equation we would have there is the EMF of the battery minus I2 R1 equals 0. So that's one equation we could have. And then another path through the battery, if we take this outside loop, getting back to A, would be the EMF minus I3 R2 equals 0. Okay, and then we also have a third equation that we could do, and that is at this junction here, right here. So into that junction we have I1 going in, and then out of that junction we have I2 and I3. So I1 is equal to I2 plus I3. Okay, so those are the rules, and we've did several problems where you generate these equations, and we have 3 unknowns, like they give you the EMF and the 2 R's and all that kind of stuff. This would be kind of a complicated way to do it, but you do have 3 equations and 3 unknowns if you're looking for all the currents. Now on this AP test, they're not going to ask you to do 10 or 15 minutes of calculations. They're short questions, okay? But you may, see a relationship there that you might not have seen before between those 3. So they may ask about changing a resistance or something like that. And this also, just looking at this loop rule, makes you realize that the voltage drop across R1, which is the current through it times its resistance, has to equal the EMF, and the voltage drop across R2 also has to equal the EMF in this case. So that's a good example of a simple parallel circuit. Okay. so now let's talk a little bit about internal resistance and ideal batteries versus real batteries. So the two circuits we just did were ideal batteries. So an ideal battery has an EMF. Okay. Okay. A real battery, okay, has an EMF, but there's also a little bit of resistance. As current goes through the battery, it doesn't move without resistance. So a real battery has an EMF plus internal resistance. Okay, and so they always use little r for the internal resistance. So we use big R usually to represent regular resistors. Little r is the internal resistance. Okay. So what this means is the actual battery, if I were drawing like the case of the battery around here in a physical representation, it would go something like this. Okay, so that would be the battery. Would be those two things put together. And so in the ideal case, whatever the EMF is, so let's say we have an EMF here, and let's say we have an EMF of 3 volts and a resistance equal to 2 ohms, something like that. Then in the ideal case, the current is going to be really simple. Okay, it's just going to be the EMF over the resistance. So we're going to have 3 over 2, so we're going to have 1.5 amps of current. Okay. And a lot of times that we do deal with ideal batteries, probably far more often than not. But sometimes they talk about a real battery with internal resistance. So what's going to go on here is if you look at that battery, if the side of your battery says 3 volts, then that basically means the EMF is equal to 3 volts. Okay. But once you hook it up to a resistor and current starts flowing, there's going to be some voltage drop due to the internal resistance, little r. So what that means is that if you take your voltmeter, okay, remember with a voltmeter you would just put that like there and there. If you put the leads of your voltmeter on either end of the battery, it's not going to read exactly 3 volts. It's going to be a little less than 3 volts. Because it's reading the EMF minus the voltage drop right there. Okay, so it's going to be ever so slight. So a lot of times the question is, what is the internal resistance? Okay, and so basically we're just using the loop rule, so that if we know what the current is, then we can usually figure out what the internal resistance is. So if we are using the loop rule for this, this is a good example of an equation we can set up. I'm not going to give you a bunch of details. So again, let's say we start from A like we usually do, and I always go clockwise. I'm going with the current. Okay, so I is going to be going this way back toward the battery. So if I start from A, if we go clockwise from A, we're going to have minus I times the internal resistance plus the EMF minus I times big R is going to equal 0. Okay, so that's the idea there with internal resistance. Okay, so that is not it's not common all the time, but it's not really uncommon either. So maybe 25% of the questions will have an internal resistance. So I wanted to bring that up and remind you of what that is. Okay. Now capacitor circuits, we have series and parallel. Okay, so very quickly, again we have an EMF here, although sometimes they just talk about a voltage V. It kind of depends. So remember, in series in capacitor circuits, their behavior, these are in series, and so remember the equivalent capacitance in series the rules are kind of switched for resistors. So in resistors, the equivalent resistance in series, you just add them up. This one you do the 1 over C1 plus 1 over C2 kind of thing. Okay. Remember that each of them will have a charge Q, and the two Q's actually I don't need to do that because in series the two Q's are the same. So each has the same charge. And because we know that the voltage across a capacitor is equal to Q over the capacitance, we know the EMF, again using the loop rule, has to equal the V1 plus V2. So that would be the same as Q over C1 plus Q over C2. And in parallel, we know, again, if you think about the loop rule, as we go around each way, the thing that has to be the same is the voltage drop across each one. There are two paths, and because of the loop rule, we know that V1 has to equal V2, and they both have to equal that. So you could also say that this is going to have, that since they have different capacitances, they might have different charges on them. So Q1 over C1 has to equal Q2 over C2, and those both have to equal the EMF. This is, of course, when they're fully charged. And the equivalent capacitance is just equal to C1 plus C2, and so on. So I don't want to go into too much detail because, again, they aren't going to have you do a bunch of calculations, but I want you to think in terms of the loop rule and such. Okay. And then we get to RC circuits. So RC circuits, we usually have an EMF, we have a capacitor and a resistor, and we did this not too long ago, so hopefully these are fairly fresh in your mind. But remember the charging circuit, we take this switch and we set it up there. Okay, and just remember with RC circuits that we have two states that we're really talking about, and then we kind of fill in, connect the dots in between. Okay, but we can remember when the switch is first closed, basically C has no resistance. It's like there's a wire in there. Okay, so it's really just like a circuit with the resistor and the EMF, and it's like there's a wire there, there's no resistance, so the current is going to equal E over R. Okay, and after a long time, so remember when we hook this up, instead of a resistor, when we put a bulb in there, when you first close the switch, the bulb is bright, and then it goes dimmer and dimmer and dimmer and goes out. So as the capacitor charges up, it finally reaches a maximum. And so that after a long time, basically C has infinite resistance, which means that I is equal to 0, and the voltage across the capacitor equal to the EMF. Okay, there's no current, there's no voltage drop across the resistor anymore because there's no current, so that means all the voltage drop is there in that. Alright, and there are two graphs that we want to look at, the charge and the current over time. Okay, so looking at our relationships here, so the current starts off at E over R, and then it eventually goes down to 0, so we have this nice exponential thing, and it's going to approach 0 as an asymptote. They might ask you to label that point on there. We would label that as E over R. Okay, and then with the charge, remember the charge starts at 0, and then there's a maximum amount of charge. So that's the exponential like that. Okay, and so the maximum amount of charge that you get, we know that Q is equal to C times V, so that is equal to C times the EMF. Okay, and the other thing that you want to do is, if we can do some quantitative reasoning here, is that the time constant is equal to R times C, and remember that's the, as we usually start off with at 0 charge on here, time for 63% charge. So if we're looking at this charge graph, we know that the when we get up to 63% or 0.63 CE, then that means the time constant, one time constant is passed, and remember the time constant is called tau. Okay. So sometimes you have to estimate that a little bit. If they give you a graph with numbers, you might have to estimate the time constant. Also remember that I is equal to dq dt. Okay, and so when you look at this, the current here is positive, but it is getting closer to 0. The slope here is positive and then getting closer to 0. Now when you're discharging, that's when we have fully charged this, and then we move that switch there. So in discharging, similar kind of thing, we're going to start off with a maximum charge, and I have to say charging is more the thing that we do. So we're going to have that maximum charge, and then it's going to approach 0, and the current, okay, again is dq dt. Now usually they talk about the magnitude of the current because this is negative slope, so the current would be in negative direction, opposite the direction we considered the first time, but usually we just talk about the magnitude. So when you first close that switch, it's actually going to be, it's going to still look like this. So our first there is going to be the voltage across the capacitor over R, which is still going to be E over R when we first close that. Okay, and our maximum charge is still CE. But I will say I think charging is far more common than discharging when we do this. Again, in the time you have, they're going to go, and also just the format of the test, they're not going to have long derivations. I think they're going to ask you questions that you can do a lot of explaining in words, rather than doing a long derivation. Okay. And the last slide I have on here is I just want you to think about weird circuits. Anything, you know, with multiple batteries, multiple resistors, just things you haven't seen before. They are very good at coming up with relatively simple circuits, but things that you do not typically see in your homework questions. So in this case, we've got an EMF there, an EMF there, and an EMF there. And so what I just want to think about is the loop rule here. That's the big thing on this. So that, again, there are two paths around the circuit, so we could make two equations here. And we have to pick a direction for current. So I tend to always pick the clockwise direction, so I'm going to call that I1. I'm going to have I2, and we're going to have I3. Now with multiple batteries like this, I don't know if those are realistic for the directions. Remember, if you had to do all the math, you might come out with a negative value for a current like I2. I'm not sure if it's really going that direction or not. It depends a lot on what the EMFs are. But that's okay. So when you're doing the loop rule, you decide which direction you think the current is going, and into this junction you do have to have, well, I mean, you can just have to, it has to make sense. You can't have all three currents going into there or all three currents going out. That doesn't make a lot of sense. But aside from that, everything else works pretty simply. So one path is I'm going to start here and I'm going to go around that way. So one equation we could have. Now remember, I'm looking at this, so starting from A, so the first path we're going to have is EMF number one is going to be positive because we're going from negative to positive there. In the direction of the current is going to be a minus I1 R1. In the direction of the current there is going to be minus I2 R2. And this one, with this EMF, you have to be careful because that's going to be a negative because you're going from the positive to the negative. So that's going to be minus E2. All those equal 0. So that's one equation that you can have. And then you can go around the outside loop. Okay. And again, we would have E1 minus I1 R1. Okay. And then we'd have a minus E3, okay, and then a minus I3 R3 equals 0. So again, I don't want to go into a lot of details, but remember, if you're stuck, I want you to have a strategy. If you're stuck, use the loop rule. See what you can do with that. Like I said, even if you're not going to get all 12 points or whatever for that question, you might be able to pick up an extra 3 or 4 just doing that, and hopefully by doing that you kind of figure out what's going on in this circuit. Okay. The only thing other thing I wanted to mention was one of these capacitor ones. We didn't do a lot of these. So let's say that is E1, that is E2. Okay. Now if you're using the loop rule with a capacitor, you kind of have to know which is the positive plate and the negative plate. So if you're going this way, okay, so let's say this is positive and that is negative. So it's kind of like looking at one of these EMF sources. Okay, so if you consider the current to be going this way, then when you're doing the loop rule here, I'll start at A again. So again, this is going from negative to positive, so that's going to be a positive E1, okay, minus IR, okay. And then looking at this, if you go from positive to negative, that's also going to be a minus. So it's kind of like, so we're going to have minus the voltage drop across C. And then we're going to have another minus here from E2. Okay, and remember for that voltage across C, that is equal to the charge over the capacitance minus E2, and so on. So that might be useful. Okay, so hopefully that covers a lot of that and reminds you of some of the things that you may see on the AP exam.